Essential NMR theory. Have you got it? This short video quiz assesses your knowledge of some of the basic aspects of NMR spectroscopy, what nuclei we are talking about, and what the basic NMR experiment involves. Your ability to use the terms frequency, chemical shift, upfield, downfield, shielded, and deshielded properly, and your ability to determine the number of sets of equivalent protons in a chemical structure, thus possibly ruling it out as a match to a given NMR spectrum. This quiz consists of 3 questions. It's meant to be taken after you have studied the material and think you understand it. During the presentation, you'll be asked to pause the video to at least try to solve the problem yourself, and only then to continue. It won't be hardly as effective if you jump to the solution immediately. Okay, here we go. Number 1, fill in the blanks below, referring to the graph on the right. Pause the video while you answer this question. Okay, in an NMR experiment, the sample is placed in a very strong magnetic field, causing the atoms with non-zero nuclear spin to either align with or against the applied field. The stronger the field, the greater the separation of the 2 nuclear states, alpha and beta. By exposing the nuclei to an intense but very short 13 microsecond pulse of radio frequency, RF energy, a non-equilibrium distribution of nuclei having the 2 states is produced. After the pulse, the antenna used to transmit it, the probe, is switched to receive mode, and very faint signals from all the resonant nuclei in the sample are received over the course of several seconds. Number 2, fill in the blanks below, referring to the graph on the right. Pause the video, and I'll read this to you when you resume. Okay. Even though the nuclei may be all protons, for example, they will absorb and then re-emit slightly different RF energies because of their differing electronic environments. Basically, different nuclei experience slightly different magnetic fields. The result is the phenomenon we call chemical shift, and it produces a range of signals, not just one. It is this NMR spectrum that provides information we desire about the compound structure. The scale on this graph is referred to by the Greek letter delta and is in the unitless units of ppm, or parts per million. In the spectrum shown here, there are 5 sets of equivalent hydrogens. 2 sets around delta 7 parts per million are furthest downfield, most deshielded, while the signal around delta 1.2 is the most shielded, or upfield, either one. Okay. So over here on our graph toward the right, this is shielded. Toward the left is deshielded. We say that shielded is upfield and deshielded is downfield. All right, well, let's take a little break here. The signal coming out of an NMR sample can be thought of as an audio signal in the range of 0 to about 4,800 hertz for a 400 megahertz instrument, riding on the carrier frequency of 400 megahertz. It's basically a voice print of the molecule. Software in the computer controlling the instrument, the console, can decode this signal and report out exactly how much of each frequency was emitted. That's the spectrum. But we don't have to do that. With the right tools, we can listen to it ourselves. Let's do that. Here's the sound of cyclohexane. Pretty much a pure tone because it's a single frequency. Notice that it's coming at about 1.5 parts per million. And we would say this is a well-shielded signal. In fact, not much else comes in this region around 1 to 2, except simple alkanes. Okay, here's another one. Ethyl acetate. Here we have 3 groups of protons. It's a little different. Can you hear the ringing? Can you hear the multiple frequencies in that? Your ear can basically take a voice print, a multitude of frequencies, and decode it just like the NMR spectrometer, and be able to sense that there are multiple frequencies in there of different magnitudes. In this case, you see we have 3 different chemical shifts. Here again, we see a proton that's pretty much just an alkyl proton, the CH3, showing up in this region around where alkanes show up, around 1. But associated with it is also a CH2, and that CH2 is way over here at 4, much further downfield, because it is de-shielded by the O. This oxygen is pulling electrons toward it, and the result is the CH2 is moved downfield. And finally, on the other side of the carbonyl group, we have a CH3 group, and this CH3 group is appearing right here around 2, in a region right around 2 that is typical of protons that are on carbons next to carbonyl groups. And again, that's because there is electron density being pulled toward that oxygen away from the hydrogen that's connected to the carbon, somewhat de-shielding it relative to alkanes. How about one more? Here's a pretty interesting compound. Inositol. How's that for a molecule? Let's listen. What we've got here, you can see, is 6 OH groups, and they're on carbons, each of which has a hydrogen. Now, the OH groups themselves, we actually cannot see in the NMR, because this sample was carried out in D2O as solvent, and what's happened is the D2O has exchanged its deuterium with the OHs, and actually all of these right now are deuterium. We see some OH in the form of DOH, but that's not really the OH of our molecule. What we're seeing in this signal is all of the H's around the cyclohexane ring. And you can see that there's 1, 2, 3, 4 different groups, 4 different types of hydrogen in this particular molecule. Okay, so the process of producing an NMR spectrum from the free induction decay, the FID, is precisely the process of determining the intensities of the frequency components of any audio wave. Mathematically, it's called a Fourier transform. Basically, what we have over here on the spectrum is a frequency analysis showing that multiple frequencies are components of this very rapidly oscillating and decaying sinusoidal audio signal. And you can see this gradual decrease in intensity as time goes by, and this basically takes maybe 2 to 3 seconds to decay. And once it's decayed, we hit it again with this 13 microsecond pulse. Take another sample, take another sample, take another sample, until we feel we have enough data. Then that data is passed to the console runs a Fourier transform, and we get our spectrum. Okay, here's the challenge. Matching an H1 NMR spectrum to a compound starts with considering how many sets of chemically equivalent protons are in a compound and seeing if that matches what we see in the spectrum. Based solely on this idea, which isomers of inositol cannot correspond to the spectrum shown on the right, which has 4 NMR signals? These are CH only. OH groups are not observable in this spectrum. Okay, pause the video. Think about this. How do you get 4 signals, 4 different kinds, and only 4 different kinds of CH protons from these various structures? Let's see what you can do. Pause the video, and I'll be with you in a minute. Okay, here we go. The goal here is to find out how many equivalent hydrogens there are. And so I'm not going to draw in all the hydrogens except this once, but we're talking about the hydrogens that would be like this. Now, what I'm going to do is I'm going to kind of cheat. I'm not going to look at the hydrogens. I'm going to look at the OHs because they're just opposite all the hydrogens, if that's okay with you. That'll just keep this thing from being too messy. Okay, in this first compound, we notice, first of all, that there's a plane of symmetry going this way, and there's also a plane of symmetry going this way. So everything on the top is the same as everything on the bottom, and everything on the right is the same as everything on the left. Well, that means that we have a signal for this one and a signal for this one, and that's it. There's just 2 different kinds of hydrogens here. How about this next one? All right. Well, what do you think? I think there's an axis of rotation through here that makes the top equivalent to the bottom. When I rotate it around, everything on the bottom becomes everything on the top. But there isn't a plane of symmetry, and there isn't an axis symmetry any other way. So in this case, we have 3 different signals. We have an H, for example, that is on the same side of the OH. That's the top one. And we have an H next to it, which is opposite it. So those are different. And we have this H in the middle here, which is cis to one of those H's, but trans to the other H. So it's in a completely different environment. The point is, we have 3 signals here. Okay, the next one, Myo. Well, can you see it? Basically, there's a plane of symmetry through right here. So there's 1 signal here, 1 signal here. These 2 are the same, and these 2 are the same. So here we have one that has 4 different signals, and that fits our pattern. So there's one possibility. How about this one over here? Well, do you see a plane of symmetry? So, right through here, right? Check this out. There's this also plane of symmetry through here. Oh, wait a minute. There's also a plane of symmetry through here. Whoa! So, the one on the left over here is the same as the one on the right. And that one's the same as this one. And actually, that one, if there's like a C2 axis here. This one on the bottom is the same as this one on the top. Well, this one on the top is the same as there's only 1 signal here. Those are all equivalent positions. Actually, if you think about it, they're all axial, aren't they? All those OHs are equatorial around the ring, and all the hydrogens are axial. And they're just all the same. Okay, down here on the left, epi. Well, we've got a plane of symmetry here. So the one on the left here is the same as the one on the right. On the bottom, left and right. And then there's one here, and there's one here. Is that right? I think so. So here's one that has 4, and it's a possibility for this structure. All right, I think you can see this next one. All the hydrogens that are up here are all equivalent. Here's another structure that has just one kind of hydrogen. Keeping going. Neo. Here's a plane of symmetry here. Any other planes of symmetry? Don't think so. But here's an axis of symmetry. If I rotate this around, all the three OHs, which are on the bottom that are down, become OHs on the top, which are up. And all the OHs that are on the top that are up become OHs that are down. So in this case, these two hydrogens on the left are the same, and those are also the same as these. And these two on the top and the bottom are also the same. So we have two different kinds of hydrogen. And finally, this allo, there's a plane of symmetry there, but that makes these two the same. It makes these two the same, and it makes these two the same. So this one has three. So I think what we conclude is that there are two structures that could be this NMR spectrum, the myo and the epi. Let's take another look at them, just in terms of their H's, and see what we can learn. Remember, in the myo, there's a plane of symmetry right through here. We have an H up and an H up on that plane. And then H down on either sides over here, and H up on either side over here. So that's what gave us the 1, 2, 3, 4 different hydrogens. And what about for epi over? Well, in the epi case, the plane of symmetry is like this. And in that case, there's an H up here, which is down, and an H down here, which is up. And flanking those are a bunch of H's that are up. And so, once again, we have this situation where we have two on the plane, which are different, because one is on the opposite side of all four of these H's, and the other one is on the same side as all of those H's. So that those two are different. And then we have the two H's coming across here, opposite the H on the plane, near it, and these H's over here, which are on the same side as the H next to it. Now, here's one of the things about these equivalent sets, the sets of equivalent hydrogens. You should always be able to state the difference in words, like I just did, where I say, okay, these two hydrogens up here, these are across from each other, so they're the same, but they're on the opposite face as the H that's next to them. Whereas these hydrogens down here are opposite each other of the plane, but they are on the same side as the hydrogen that's next to them. Do you see how we could actually say that in words and get some meaningful statement of how they're different? That's how that works. Now, just for fun, if we know a little bit more, more than we know right now, we actually might be able to know which one this is. I'm going to go ahead and draw the structures of these two as cyclohexane chairs. Myo, what have we got here? Well, we've got 4 OHs down and 2 OHs up. I think we can get 4 of these to be equatorial and 2 of them to be axial. Okay, so let's see. Now we're just looking at the OHs. So basically, I think we could go equatorial, 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 and then on the same side, axial. Right, so this is OH, like that, see? And then let's see what this epi is all about. Well, let's see, they're all on the same side except one. If we make sure that that one is equatorial up here, then this would be equatorial, equatorial, axial, equatorial, axial. Is that it? 2 axials and an equatorial. Okay, so that's this. And now if we draw in the H's, and we draw these H's, they're there. Now this one over here, this is the epi, right? And this one is the myo. And believe it or not, I can tell which one of these this is because there's a very special relationship here. These three hydrogens, this one's trans, and this is trans, and they're trans diaxial. And there's two relationships like that. In epi, we have this trans axial business at these three carbons over here. And in the myo, we have that over here, and we have it over here. There's two different places where we have this. That's interesting. And actually, I can tell that because this wide separation here, this is two H's that are like this, anti to each other, axially. And there's one H here. It's just smaller. So I know that that's 2H and this is 1H. There are 6 H's in here. So these tall ones, this is a group of 2 H's. This is 2H, this is 1H, and this is 1H. I'm just thinking out loud here as I solve this. And this can only be the myo. Okay, there you go. That's how it works. Remember, except for a few nuclei that have both an even number of protons and an even number of neutrons, C12, for instance, 6 protons and 6 neutrons, all other nuclei can be observed by NMR spectroscopy. Most notably, proton and C13 NMR are particularly informative in relation to chemical structure. Fourier transformation of the raw free induction decay provides the spectrum we analyze. Protons in different chemical, that means electronic environments, have different chemical shifts and can be referred to as shielded or upfield and deshielded or downfield relative to each other. The number of sets of equivalent protons in a chemical structure can be used to rule out that structure as a match to an NMR spectrum. Okay, well, I hope that helped, and I hope you've got it.